Hey everybody, welcome to Techforpsych, where we combine the latest in neurotechnology with ancient wisdom to supercharge your brain. I've got a very special video for you today. We're taking a look at Obelab's functional near-infrared spectroscopy device that uses near-infrared light to track blood flow of the brain. This is functional MRI-like capabilities in the form of a wearable. I met up with the Chief Operating Officer, Han-Sik Yoon, in order to answer a number of questions and take me through a trial run with different cognitive tasks using this amazing device. Stay tuned for all that and more in this episode of Techforpsych. Hey everybody, I've got Han-Sik here from South Korea, the Chief Operating Officer of Obelab, which has created this functional near-infrared spectroscopy device you can wear on your head, completely revolutionary. We were talking about the difference between this device, EEG, and functional MRI, and I was hoping you'd be able to give us an overview of how this technology is so unique in that respect for brain imaging.
Sure, Cody. So our device is an fNIRS device, and you may know that we have a few different modalities for neuroimaging.
Yeah.
Firstly, fMRI. fMRI, of course, is considered as a gold standard. It provides the highest resolution, but it still has some shortcomings. It's very expensive, it's stationary, so not accessible to all the people. And if you talk about EEG, EEG is also prevalently used in research and clinical settings, but still EEG involves a lot of noise, and it doesn't provide as high spatial resolution as fMRI or fNIRS does.
Yeah, and EEG is hard to locate where exactly things are going on, right? I imagine this has better spatial resolution than EEG, right?
So fNIRS, I think, generally provides a little bit better spatial resolution than EEG, but when talking about our device, we specially designed the sensor arrays and also applied a new algorithm so that even with the limited amount of optical components, you'll be able to get the highest resolution for fNIRS.
And the sensors here in the forehead region, they go over the forehead region. This is a combination of both light and sensors, right? Could you explain how that works? It's emitting the light, right, and bounces back and is analyzed? Could you explain how that works?
So fNIRS measures the changes of oxygen, and when neuron fires, it uses oxygen, and through blood flow, you provide more oxygen. So the area of activation actually has more activation, increased oxygen. And using near-infrared light, you can actually measure the changes in oxygen levels by emitting the light into the brain cortex and getting back the light and measuring the remaining power, which tells you how the oxygen levels are changing in the brain cortex.
And to be able to make this into a form of a wearable where people can engage with that type of information at home and in research institutions is unbelievable. So there's other functional near-infrared devices, right? These have been used in research laboratories and academic institutions, but this, in my opinion, is one of the first times the only time I've seen it as like a commercial product. How did you guys go from the laboratory to actually being able to create a product that people can use on the ground level and have access to it? How did that happen?
Sure, that actually comes from our background. Our company is a university spin-off from the leading engineering school, engineering university in Korea, which is KAIST. So they're able to come up with the world's first dedicated integrated circuit for NIRS device. So that's why we are able to come up with this portable device.
And you guys have used this for a lot of different things, right?
Sure.
Neuroscience studies. What are some of the studies that you guys have done and some of the practical applications that you've been involved with so far?
So we're actually targeting this device to become a clinical device, which was not the case for fNIRS so far. And we think that it's possible with this type of form factor because it's easy to use in clinical settings. So we are, but for now, we are still doing clinical trials in order to validate.
So what are you looking at for FDA use for this? What would you use to diagnose or track in the brain?
So we are actually starting from Korea, and we are doing clinical trials on depression and Alzheimer's disease.
Amazing, because obviously the frontal lobe is so important in both of those disorders, right? So if you have low functioning of those areas, then it's going to be a diagnostic tool, right?
Exactly.
And any use in some of those EEG devices are being used for meditation. So I started thinking about, you know, in meditation there's something called hypofrontality where the frontal lobe kind of quiets down. Has anybody engaged in that with this device as well?
Well, we have just did a quick pilot study in Korea, and we've interestingly found that the difference between the trained group for meditation and who are the beginners. So the beginners, they showed less amount of difference between the random thinking and meditation, whereas the experts or trained groups showed a huge difference between the random thinking and meditation. As you said, firstly, they showed hypoactivation during the meditation, and also they showed much increased connectivity during the meditation.
Connectivity, you can actually see connectivity between different areas of the frontal lobe?
Yes.
Okay.
If you do a little bit of analysis using the data that you measure using our device, you can do the connectivity analysis.
So you guys are really trying to revolutionize what's going on in brain imaging right now, because functional MRI, which is used for all the big fancy neuroscience and mental health studies, is so expensive, and you have to go into a hospital, you have to go into the room with the big magnet. What's your guys' vision for really changing how that's done with this device?
So we think that the reason for brain being uncovered much yet is because there is less amount of data. With the ease of use and the affordability that our device provides, we'll be able to collect big data and use it to figure out how brain is functioning better than before. And from that, we want to create a lot of different applications.
And when will this be available in general for people to start using?
Well, this is already in the market since 2016, and we actually got Korea FDA approval in 2017. So it's widely used in hospitals and research centers in Korea. We also have a few customers in US. I hope that we can expand our presence in the US soon.
All right, so we've got Obelab's fNIRS device. Take me through, how does this thing work? We've got the tablet set up.
Of course. It's very easy to use. So firstly, you just put this on subject's head and make sure that it's well aligned, and just tighten it up for good contact.
Oh, it's really comfortable.
Is it?
Yeah.
Feel good?
Yeah, it does feel good. It's very soft on the head.
All right. So we connect this device with tablet or even notebook PC using Wi-Fi. And now you see that the device is connected, scanned, and just select it and connect. And then the first step, really, before starting the measurement, is doing the gain calibration. Through gain calibration, what we're doing is actually adjust the power of the light source according to different skin colors and thickness of skulls, and also adjust the gain of detectors.
I was trying not to move there because I wasn't sure if it was trying to. You need to be still when it's doing that? Is it important to be still when it's doing that?
Right. It's better not to move during the gain calibration.
And the little red circles, was that which sensors specifically needed to be calibrated, or was that the light sources? Like which one? What's the difference between red and blue?
So the red circles indicate light sources. Blue indicates detectors.
Okay.
So after the gain calibration, you'll see which channels are rejected. The ones without yellow circles are rejected because of the lower SNR than set threshold.
Okay.
So now you see that you have many channels rejected. In such case, you put readjust the device so that it gets a little bit better contact.
And you usually just tighten it up?
Right. Usually just tighten it up will be good enough. All right. Now retry the gain calibration. It's slightly better, and we recommend researchers to move forward from here if you get around or less than 5 channels rejected.
Okay, so yellow means that they've been accepted.
Yes.
Okay. Sounds good.
All right.
And what are these bars here?
These bars are a histogram showing the number of channels in each SNR range, signal to noise ranges.
Okay. Great.
So after 5 seconds of initialization, we start the measurement. And now showing the activation in color map. So if the color map turns into yellow and red, it means the oxygen levels are increasing, which means your brain is being activated in that region. And if it decreases, the color turns into blue.
So should I try to think of a math problem or something?
Yeah, I can give you a few math problems.
Okay.
So 5 by 7.
5 divided by 7? Or 5 times 7?
5 times 7.
35?
12 times 15. It's getting a little bit difficult.
Man, I was never that great at no, don't take out your calculator. No, I can do that. 12 times 15. So 120.
You're already working hard.
Yeah. All right, let's skip that one.
All right.
Think about it later.
I think this is good enough.
Yeah, I see a lot of
already really working hard.
I was never very good at calculations like that.
All right. Try to get rest, relaxed a little bit.
I'll sit back.
Then we'll be able to see that it goes back to the baseline.
Yeah.
Wow. Yeah.
That's amazing.
So the basic mode is 3D map, heat map, or color map mode, but you can also display this in a time series manner. So by all channel, you see oxyhemoglobin and deoxyhemoglobin changes in red color graph and blue color graph, respectively.
Wow.
And the ones with just the blue color without changing, those channels are actually rejected.
Okay.
Right. And we already removed the heartbeat, so If you don't remove it, you'll see oscillations like this.
Oh, wow, okay.
And basically, we do the MBLM, modified Beer-Lambert law, to calculate the oxy and deoxyhemoglobin concentration changes. But we also implemented an algorithm called diffuse optical tomography, which is an image reconstruction technology. And by doing that, you'll be able to see the activation by layers, starting from the skin level until the cortex level, in a much granular mode. And
can you tell depth of where these are occurring in the cortex, or is it kind of just a uniform depth that we're looking at?
So you can select the depth from here. The deepest layer is 1.8, which means from 1.6 to 2.0 centimeters.
Wow. And that's pretty much the majority of the human cortex, right?
It is, it is.
Wow. Amazing.
And by default, we are actually monitoring oxyhemoglobin concentration changes in the color map, but you can change it to deoxyhemoglobin concentration and total hemoglobin concentration changes. And you can also select the average mode just to compare the average activation of left and right hemisphere.
Wow, that would be really helpful for meditation, because I know that there's differences. Even in depression, there's supposed to be asymmetry, right, in the frontal lobe?
Right. And actually, the researchers typically use a laptop than the tablet, because it can actually synchronize with external stimuli programs. But in case you want to use the tablet, you can manually do the timestamping by tapping the task buttons. When you start the task button, you tap the task button, and when you are done with the task, you tap it again. Okay,
so that way during your time series you can know when you're actually doing the task.
Sure. So that you can do the analysis.
Yeah. And it's recording right now? It's been recording the whole time?
Yeah, it's recording right now.
Wow. Oh, and you can swirl the brain.
You can rotate a little bit.
And you can see that it's mostly just the frontal lobe that we're
just the
looking
frontal
at
lobe. And grid. So you may be able to see the numbers here, which indicates the number of channels. So you'll be able to see which channel location is getting more activation.
Oh, wow. You can see the individual sensors, okay.
And this is just for monitoring real-time monitoring purpose, but you can set the baseline whenever you want to. So if you want to compare from a certain time point, and after that, you just tap the baseline, and then you'll be able to see the relative changes since then.
Okay. So it's all statistics, all mapping out different levels of brain activation. And then are there, when you're done recording, can you see the course of a?
Sure. So when you're done, just tap the done button, and you can put some informations here.
Just to label the recording?
Yeah, just label the recording. And you're done. And if you want to access to the data you have just measured and saved, you can go to save data, and the most recent data is at the top. So this is the one that we just finished the measurement, and you can actually replay.
Okay.
And you can fast forward it a little bit.
Okay. Relive the experience.
And you see the markers here.
Uh-huh. Is that where we did the
test buttons?
Mm-hmm. Okay. Very cool.
And you of course can export the data from tablet to PC or notebook for post-processing. You can do a lot of different analysis using our proprietary analysis tool.
Mm-hmm.
It's really easy to use comparing to the other tools in the market.
Other fNIRS tools?
fNIRS analysis tools.
Mm-hmm.
So even the researchers who don't have much experience in analyzing these kind of data
mm-hmm.
can easily do the research.
So this is the Obelab functional infrared device, and I wanted to do a monologue before I left the hotel here, just because this device is, in my opinion, the future of neuroimaging. As Hansuk said before, one of the reasons why neuroscience and brain imaging data hasn't come into general use amongst various applications to include brain-computer interface, diagnosing psychiatric and brain disorders, tracking attention, neurofeedback. All these applications are really going to be taken to the next level by this type of technology. EEG, although great and very applicable for our needs now, can have a lot of noise within it and not be as precise as a lot of people think that near-infrared light could be or is currently. I mean, look at me, I'm wearing a near-infrared spectroscopy device in my head right now, and it's mobile, and it's mobile, and it's mobile communicating with this tablet. This is the future, this is where we're headed. Hopefully with time, the price of these devices can come down so that right now it's in the hands of the research institutions and the academic laboratories doing great things like getting FDA approved in South Korea, and hopefully getting medical applications very soon here in the US as well. But as this technology improves, just like the other devices, I could see the price eventually coming down, and general people being able to have more access to this type of technology. And as you saw during the demonstration, you can track things like hypofrontality with this device, which is the quieting of the frontal lobes, and that could be indicated in diagnosing depression, Alzheimer's, like they're doing in South Korea right now with this device, with trials underway. But then also tracking attention, or meditative states of mind, or any other types of states of mind that we can do in neurocognitive training. So the fact that they're able to use near-infrared light to track the blood flow changes is exactly what I've been talking about on this channel for some time now. Functional MRI-like capabilities in the form of a wearable right here with Obelab's fNIRS device. So I really want to thank Obelab for showing me this device, and you make me so excited for the future and where we're headed. So I'm so excited to see what happens in the next couple of years with this type of technology, and here it is happening before our eyes. Functional MRI-like capabilities of the frontal lobe communicating to a tablet in the form of a wearable. Amazing. Hey everybody, I just wanted to focus on the science of the fNIRS device in this video, but in future videos that are coming very soon, I'll dive deeper into the pricing structure so we can look at how to bring this device to the average consumer rather than just having it limited to clinics, research institutions, and academic environments.